Dear students, the next topic of our discussion is Poisson's equation and Laplace equation. We have seen these equations in the first unit. We know the electric field, and the electric field can be written as a gradient of a scalar potential. That is, E can be written as minus del V. The last class we have discussed it. We have proved this equation also. Okay. This is equation number 1. Then we know the Gauss's law in differential form. That is, divergence of this electric field, that is equal to rho by epsilon 0. Let me put this as equation 2. Now I am replacing this E by this expression, that is del divergence of minus del V, that is equal to rho by epsilon 0. That is, if I take a minus outside, del dot del, that will be del square. This will be del square V is equal to rho by epsilon 0. That is, if I take the minus sign right side, this is del square V is equal to minus rho by epsilon 0. This equation is called Poisson equation. If you know the electric potential in a region, then you can find out the charge density rho in that region. That is the beauty of this equation. Different form of del square we have already seen in the first unit, that is in the cylindrical polar coordinates, in the spherical polar coordinates, and also in the Cartesian coordinate system. In the problems, we have to use all those forms. Generally, we can write this as a del square. Okay. Now, in the region, the charge density is 0. Where rho is equal to 0, then the above Poisson equation reduces to del square V is equal to 0, because right hand side is 0. This is called Laplace equation. Okay, we will do a few problems later. Now let us go to the next topic, that is a potential due to a localized charge distribution. That is, the electric potential due to a localized charge distribution. We know that the electric potential due to a point charge, that is 1 by 4 pi epsilon 0 q by r. This is a potential due to a point charge. Then potential due to a small amount of charge dq. That can be written as dV, that is equal to 1 by 4 pi epsilon 0 dq by r. We know that different form of the charge density, that is a volume charge density rho, is if rho is equal to volume charge density dq by dV. From this one can write dq is equal to rho dV. Then potential due to a small amount of charge dq contained in the small volume element dV, that can be written as V is equal to 1 by 4 pi epsilon 0 integration. Instead of dq, you have to substitute the rho dV here, then do the integration. Then you will get this result, that is integration rho dV divided by r. This is a volume integration. Here, be careful, this is a volume, not the electric potential. Okay, this is a electric potential due to a volume charge density. Now, potential due to the surface charge distribution. That is, if sigma is the surface charge density, that will be dq by dA, and from this one can write dq is equal to sigma dA, and one can easily write the potential due to the surface charge distribution, that is 1 by 4 pi epsilon 0 into integration. Instead of dq we have to substitute sigma dA by r. This is the surface charge density. This is the surface area. Then potential due to line charge distribution. That is, if lambda is a linear charge density, that is dq by dl, then from this one can write dq is equal to lambda dl. The potential due to the line charge distribution can be written as 1 by 4 pi epsilon 0 integration lambda dl divided by r. Fine. We will find out the electric potential due to the this volume charge density and surface charge density and the linear charge density distributions later. Now let us move to the another topic, that is work and energy in electrostatics. That is the work and energy in electrostatics. Here we will describe what is the work and what is the energy in electrostatics, and the first one that we will do in this section is we will calculate the work done to move a charge. We know the work energy theorem in physics. That is, wherever you want to find out the energy, in those places you have to do certain work, then those work will be stored as energy. Suppose if there is an object lying on the ground whose mass is m, this object is lying on the ground because of the gravitational force. If I want to lift this body to a certain height, then I have to apply at least a force that is in this direction. That force should be at least greater than or equal to mg, roughly let us say this mg, and we apply this force. Therefore this body is get displaced in this direction, and finally this object reaches here. That is, the work done to lift this body from the ground to this particular height h, that work is equal to force into displacement F dot d. The force and displacement are in the same direction, therefore this is mg and the height is h. That is, we know that this work is stored as the potential energy in this body. That is, once after this work the body reaches here, and this work will be stored as its potential energy. Similar way, here we will do certain work on a charge in an electric field, and that work will be stored as the energy of that charge system. That is, the work in this picture is done against the gravitational force field. Okay. The similar way, we will do the work against the electrostatic force, and that work will be stored as the energy on the electric charge system. Suppose we have a stationary configuration of source charges. That is, these are the stationary configuration of source charges. and here we have the charges, that is Q1, Q2, Q3 up to Qi, and all these charges produces an electric field in this region, and in this electric field we are moving a test charge, that is the test charge is Q, from the point A to the point B along this path. Okay, that is, let us write, we want to move a test charge Q from the point A to B along this path, and at any point along this path this charge Q experiences an electric force that is created by these source charges Q1, Q2 and Qn charges. Let me note down. That is, while moving the charge Q from here to here, that is, the charge Q experiences an electric force because of the electric field generated by the source charges. That electric force is given by F is equal to QE. Here the E is the electric field produced by the source charges. Okay, then because of this electric field there may be a repulsive force, or then to move the test charge from A to the point B, we have to apply an external force. That is, we are applying that external force, we bring the charge from the point A to B. That is a work done to bring the charge from A to B. That can be written as W, that is from A to B, F dot dl. This force is nothing but, we have written QE. Therefore A to B QE dot dl. Here the force, that force has to be done against the electric field. Therefore we have to put a minus sign. Okay, that is, there will be a repulsive force on this test charge Q, and against the repulsive force we have to apply an external force. That external force must be at least equal or greater than that of the Coulomb force. Therefore that external force must be opposite to the electrostatic force. Therefore we will put a negative sign here. Let us note here the force. The negative sign shows that the force must be done against the electric field. Fine. Now let us write this work as a, we can take minus Q outside of the integration. This will be A to B E dot dl. In the last class we have discussed one fact, that if a charge Q is here, that is a source charge, the electric field lines will be emerging away from this charge. Then in that electric field, that is, I consider 2 points. One point is here and another point is here. This is a point A and this is a point B. Then I am bringing a charge from A to B. That charge is a test charge. Let us say Q0 is equal to 1 Coulomb. Then the work done to bring the charge from A to B is written as A to B E dot dl, and the electric field at a distance A, that is generally given by 1 by 4 pi epsilon 0, that is a to b 1 by 4 pi epsilon 0 q by r. The length element is nothing but dr. That is, if I do the integration, this will be 1 by 4 pi epsilon 0 q into, here this should be r square will be there, because this is the E is the electric field produced by this source charge at a distance r. Therefore, the integration, that is from a to b 1 by r square dr, then this will give you q by 4 pi epsilon 0. This is a minus 1 by r. If I put instead of a and b, distance from the source charge to the point b is rb, to the point a is ra. This will be equal to minus q by 4 pi epsilon 0 1 by rb minus 1 by ra, or this can be written as, if I take the minus sign to the inside, this will be q by 4 pi epsilon 0 1 by ra minus 1 by rb, or q by 4 pi epsilon 0. On this I can write, if I take the q inside, then 1 by 4 pi epsilon 0 q by ra minus 1 by 4 pi epsilon 0 q by rb. We know that this term is nothing but the electric potential at a distance a. Therefore, this we can write VA minus, this is can be written as electric potential at the point B, because we know the electric potential V is equal to 1 by 4 pi epsilon 0 q by r. If I check the left hand side, the left hand side is nothing but work is equal to integration a to b e dot dl. Therefore, this I can write, this is a integration a to b e dot dl, that is equal to va minus vb. If you come back to the work, the present case, here we are also having integration a to b e dot dl. Okay. Instead of this e dot dl, I will substitute this va minus vb. Therefore, the work can be written as w is equal to minus q into va minus vb. That is, if you take the minus sign inside, it's q into vb minus va. Or I can write work done on the charge capital Q is equal to the electric potential between the 2 points. That is, the potential difference between 2 points A and B, that is equal to the work done to carry a charge from the point A to B in an electric field. Let me note down. That is, the potential difference between 2 points is defined as the work done to move a test charge from the point A to B. That is, if you come back to the picture, that is, if you do this work on this Q charge and we bring the charge from A to B, and after reaching the point B, this work will be stored as the energy in this charge system. Okay. Then if I consider the point A, that is this reference point, it is at infinity. That is, I am bringing the charge from the infinity to the point B. The point A is at infinity means that is A is at infinity. Therefore, at the infinite point, infinity means it is far away from these charges, where the electric potential is 0. That is at infinity, V infinity, that is electric potential at the infinity is 0. Or we can say the VA is equal to 0. Therefore, the final expression that you will reduces to another form, that is, if the reference point is at infinity. Present problem, the reference point is A, that is A is at infinity. The potential at the point A is equal to 0. Therefore, in this equation, this term will goes to 0. Therefore, the remaining term is W by Q. That is W by Q is equal to Vp. In general, we can write the work done on the charge Q is equal to the electric potential at that point. That is, W is nothing but QV, or simply we can write W is equal to QV. Work is equal to the charge into electric potential. This equation is quite useful, that we will use in the next session also. That is, next we will discuss the energy of a point charge distribution. That is, we are going to discuss the energy of a point charge distribution. Actually, we have a system of charges. It is Q1, Q2 and Q3. We will calculate how much work is required to assemble the entire collection of these point charges. The Q1, Q2, Q3 are the point charges, and we are assembling these charges like in this configuration. Q1 is here, Q2 is here, and Q3 is here. Qt is at a distance R12, and the charge Q3 is at a distance R13, and Q2 is at a distance R23. To assemble the charge, the point charges to this configuration, how much work has to be done? That is our question. Okay, now let us proceed. Let me write this question. That is, we are going to calculate total amount of work that is required to assemble the charges into this configuration. That is, just now we have mentioned that whatever the work we will obtain, that work will be stored as the energy in this system of charges. To assemble the charge like this one, first we have to do, there were no charges initially. At a time t is equal to 0, there was no charge. Then first we will bring charge Q1 to the point 1. We will calculate how much work is required. Then after calculating this work, we will do this work on this charge, and we will bring the charge to the point here. Then our charge will reach at this point. Next, we will bring another charge, that is Q2, to the point 2. Then we need to calculate how much work is needed to bring the charge Q2 from infinity to the point 2. Because here there will be a problem. The charge Q1 is already there. This electric field is emerging away from this charge Q1. While bringing another charge Q2 to the point 2, the charge Q1 exert some electric force on Q2. Against that electric force, we will do the work and bring the charge to the point 2. That work we have to be calculated. That work is not as W2. Therefore, the work 1 was the work done to bring the charge to the point Q1, and we will calculate what amount of work is W1, and we will calculate what amount of work is W2, and after finding out the W2, we will do that work and bring the charge to the position 2. Then, after reaching the charge to the position 2, now we have to bring the third charge to the point 3. Then we need to calculate how much work is required. That work is denoted as W3. Now the problem is quite difficult because here there are already two charges, Q1 and Q2. These two charges produces their own electric field. And in this electric field, while bringing the third charge Q3, the charge Q3 will experience a large repulsive force. Then against that repulsive force, we have to apply some external force, and we have to bring the charge Q3 to the point 3. That is, the charges at the point Q1 and Q2 produces some electric potential at the repulsive electric potential at the point 3. Then those electric potential have to be calculated. Then we have to calculate the work done. Then calculate after knowing the amount of work done. We will do that work on the charge 3 and we bring the charge to the third position. In this way, we will assemble these three charges. Okay. Then the total energy of this system, that will be equal to the work W1 plus W2 plus W3. The total work that is equal to the W1 plus W2 plus W3, that total amount of work will be stored as the energy in this charge distribution system. That is our procedure we are going to do. Now let us begin. That is, first, to assemble the charges, the three charges, first we have to bring the charge Q1 to the point 1. Is bring charge Q1 to the point 1. That is, this is assumed that this is a point 1. That is the amount of work required we have to calculate. That is we denoted as W1. That is, we are going to bring the charge Q1 from infinity to the point 1. Therefore, the work done, to find out the work done, we know that the expression is Q into V. Just now we have derived, where Q is the charge. This is a test charge. Here the test charge is Q1, that we are bringing to the position 1. The V is the potential present at the point 1, but there is no other charges near the point 1, no charge at all. Therefore, the potential at the point 1 will be 0. Therefore, we can write, that is V is the specifically we can write V1. V1 is the electric potential at the point 1. That is, you can write this is a potential at the point 1. That is, that V1 is equal to 0 because no charge is present there. Therefore, W1 can be written as Q1 into 0. That is, W1 is equal to 0. The work done, the work required to bring the charge Q1 from infinity to the point 1, that is equal to 0. That is, without much effort, we can bring the charge q1 to the position 1. Now the first charge reached in its position. Okay. Now let us calculate the amount of work required to bring the charge 2. That is, now we try to bring q2 to the point 2. I fix this is the point 2. That is, the distance to the point 2 is, I denote r12. Okay. Then to bring this charge, we need to do some certain amount of work. Let me denote that work is W2. That is, W2 is the work done to bring Q2 to the point 2. The expression or the equation to calculate the work done is W is equal to Q into V. Now we are bringing the second charge. Therefore, the first charge is Q2, and the work required to bring this charge Q2 is W2, where V is the electric potential present at the point 2. That is, we write V2. That is, V2 is the electric potential at the distance R12. That is, here, what will be the electric potential at the point 2? Will be there an electric potential? Yes, because the charge Q1 is already reached here. The Q1 charge produces an electric field at a distance 2. That is the distance R12. That electric potential we can write V1 1 by 4 pi epsilon 0 Q1. The Q1 charge produces a potential at a distance R12. The V2 at the point 2, that is electric potential at the point. Okay, let me write it as at the point. The point 2. The electric potential is produced by the charge Q1. Therefore, we can write 1 by 4 pi epsilon 0 Q1, because the electric potential is produced by the charge Q1 at a distance R12. Okay, now just to substitute the V2 here, that is, our W2 will be Q2 into 1 by 4 pi epsilon 0 Q1 divided by R12. Or I can write this W2 is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R12. This is the amount of work has to be done to bring the second charge to the position R12. Then what we will do, by calculating this work, that is the amount of work needed is W2, then we will do the work, that is we will bring the charge Q2 to the point 2. Okay, now our charge Q2 reached here. Now one more charge is left, that is third charge. So bring the third charge Q3 to the point 3. Here also we need to calculate the work done. Work done to bring the charge from infinity to the point 3, that is equal to W3. We are bringing the test charge Q3 to the point 3, where the potential is V3. That is, here Q1 is already there, Q2 is also reached. Separation between these two is R12. Now we have the third point, we have to bring the third charge Q3 to this point, and here the situation is not that much easy. That is, at the point 3, we need to calculate what is the potential at the point 3. At the point 3, the Q1 will produce an electric potential. That is, the distance from Q1 to point 3 is R13, and also the charge Q2 produces electric potential at the point 3. The distance is R23. Therefore, V3 is the electric potential at the point 3. What is the electric potential? That V3 can be written as electric potential at the point 3 due to the Q1 charge. That is, let me write electric potential at the point 3 due to the charge placed at the point 1, that is Q1 charge, plus electric potential at the point 3 due to the charge 2. This is equal to 1 by 4 pi epsilon 0. This electric potential is due to this charge 1. Therefore, I will write this as a Q1 divided by the distance from the charge 1 to the point 3. That is, we have denoted R13. This is R13 plus 1 by 4 pi epsilon 0. V32 is the electric potential at the point 3 due to the charge 2. Therefore, I will write this is a Q2. Then the distance from the charge 2 to 3. That is this distance R23 in the figure. Okay, that is R23. We have to replace this V3 by this expression. Therefore, our W3 is equal to Q3 into 1 by 4 pi epsilon 0 Q1 by R13 plus 1 by 4 pi epsilon 0 Q2 by R23. Or if I open the bracket, this will be 1 by 4 pi epsilon 0 Q1 Q3 divided by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 divided by R23. This is the amount of work done has to be done to bring the third charge to the point 3. Okay. After knowing this work, we do the work on the charge Q3 and we bring the charge Q3 to the point 3. That is, now our charge 3 is here. Fine. Then what will be the energy of the system of these point charges? That we had to calculate all this work. These are work done to bring the charge Q1 was W1, work done the charge Q2 was W2, work done to bring the charge Q3 was W3. All these three works, and this total work will be stored as the energy in this system of charges. Fine. Now, answering this question, we can write total work done to assemble the charges Q1, Q2 and Q3. That is equal to W is equal to W1 plus W2 plus W3. The first work W1, it was 0. The second work, that was this one, 1 by 4 pi epsilon 0 Q1 and Q2 by R12. And third work, that is here, 1 by 4 pi epsilon 0 Q1 Q3 divided by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 divided by R23. This is Q3. Okay. That is, I can write from this 1 by 4 pi epsilon 0 I can take outside. Then if you look at the numbers that I have written here, it is R12 here 1 and 2, R13 here 1 and 3, R23 here 2 and 3. I can write this summation over I, that is run from 1 to n if there are n number of charges. That is a first number 1, this one is 2. Okay, that is then summation second digit j is equal to run from 1 to n. Another thing, this if this is a I, this is a j is always greater than I. J is always greater than I. Therefore, here I will write j is greater than I. Okay. Then what else we can remaining? This is a qi qj, that is you can write qij by and numbers 1 and 2, that is r I j. J is not equal to I. Anywhere you cannot see R11 or R22. I is not equal to j. I would like to draw your attention to this case. That is, here we have a system of 3 charges. The total work done to assemble these charges, or that is the total energy of these charges, that can be written as 1 by 4 pi epsilon 0. That is, here we have Q1 and Q2. This Q1, Q2 divided by the separation between these two is R12 plus, now we have Q1 and Q3. Q1, Q3 divided by R13 plus, next the remaining term, we don't have this pair. That is Q2 and Q3. Q2, Q3 divided by R12. I cannot write again, that is Q3 and Q1 by R13. That will be the repetition, because this is the total energy of the system of these charges. Because if you refer the derived result, this will also give the same one. System of 3 charges, Q1, Q2, Q1, Q3, Q2, Q3. There is no term like Q3, Q3, Q1 or Q3, Q2, because those terms will be the repetition. Okay. Then in one way, that is in this way, we can write the energy of the system without repeating the term. For that we have to be very careful. We have to see whether the term is repeated or not. Then if I calculate the if I assign some numerical values and I calculate if this is a result, this term will give the result 2, and this will give the result 4, this will give the result 6, then this will be is equal to total work will be equal to 12. Then the same result I can obtain in another way. That is, I will write this work done in this way. That is, I will write here 1 by 4 pi epsilon 0. That is a nicer way to write this work done, but without taking any care. That is this one. If you have the charge Q1 and Q2, then you write first Q1, Q2 divided by R12 plus, that is, we have completed these two. Next Q1 and Q3, Q1, Q3 divided by R13. Then next Q2 and Q3. The term starting from the charge 2, because term starting from the Q1 is already completed. Q2, Q3 divided by R23. Then what else? Q2 and Q1. Q2, Q1 divided by R12. The two charges starting from Q1, Q1, Q2, Q2 is over. Similarly, we will have two terms for Q3. Q3, that is first one, Q3, Q2. Q3, Q2 divided by R23 plus next this one, Q3, Q1. Q3, Q1 divided by R13. Okay, in this way also you can write, but this is not true actually. Why? If you see, if Q1, Q2 by 1 by 4 pi epsilon 0, Q1 by Q2, if you give the answer 2, that is this term will give answer 2, and 1 by 4 pi epsilon 0, Q1, Q3 by R13, that is Q1, Q3 by R13, that will give 4, Q2, Q3, R23, that is, sorry, here I committed a mistake. This should be Q3. Okay, be careful, this is Q3, because I wrote this was a Q1, this should be Q3. Sorry for the mistake. Now Q2, Q3 by R23, this result was 6. Fine. Actually, what is the actual result? That is a 12. 12 joule is the energy of this charge configuration. Then without, if I write in this way, let us see what is the result we are obtaining. This Q2, Q1 by R12, that is this term Q2, that is, this term is nothing but this one, Q2, Q1 by R12, whose answer is 2. Okay. Now Q2, Q3 by, that is Q2, Q3 means again this time Q2, Q3 by R12. Okay, this also need to be correct. This should be R23. Q2, Q3 by R23. The answer is this is 6. Q3, Q1 by R13. This is 4. That is, if you calculate all these values, you will get 2 plus 4 plus 6 plus 2 plus 6 plus 4. 6, 12, 14, 20, 24. But what is the actual answer? Actual answer is the 12. But if you take the half of this one, if I multiply with the half, then we will get the 12. That is, here, if you write it 1 by 2, then in this way also you can write the expression for the potential energy of the system of 3 charges. Without taking any care, without considering whether the term is repeated or not. You start from one charge, then write Q1, Q2, Q1, Q3, then Q2, Q3, Q2, Q1, Q3, Q2, Q3, Q1. Then if you find out the energy, that will be also fine, but you have to divide it by half. If you, what is the advantage of writing in this way? That is, we no need to worry about whether any term is repeated or not. That is, both equations are same. The one difference is here we have to add an half, to multiply with a half. If all the terms are repeated, then here no need to write half. That is the difference. Therefore, what is my intention is, here I will write this equation as W is equal to half into 1 by 4 pi epsilon 0 summation I is equal to 1 to n j, that is equal to 1 to n. Here instead of j greater than I will make it as a simplify, that is j is not equal to I, the remaining term is qi j by rij. Fine, because both will give the same result. Here we had to taken care that j should be greater than I, but here only thing is j should not be equal to I. We are getting more relaxation if you write the work or energy in using this expression. Now what I am going to do is I am bringing this term inside the summation, therefore this is equal to half into summation I is equal to 1 to n. Then I will take the qi, sorry, this should be here qi qj. I have splitted because here we have q1 q2 like this. Okay, here also there was a mistake, this should also be qj. Okay, be careful, that is here I also corrected. Okay, I am really sorry for the mistake from my side, please correct it. This is equal to I is equal to 1 to n. I will take the qi here, qi, then summation, that is j is equal to 1, j not equal to I, n, and 1 by 4 pi epsilon 0 I write with the qj by rij. Okay, this time this is nothing but the electric potential due to a charge Vri. Okay. That is, the work here can be written as W is equal to half into summation over I is equal to 1 to n qi Vri. This is expression for the general expression for the energy stored in the charge distribution. Then for volume charge density, this is equal to W half, instead of this discrete charges, this is a continuous charge distribution, that is rho v d tau, because we know that rho is equal to dq by dv, or I will write this as a d tau in order to avoid the confusion of volume element and electric potential. Then dq is equal to rho d tau, q is equal to integration rho d tau. Please, instead of this q we have substituted integration rho d tau. V is a potential as it is. This is a volume element. This V is the electric potential. Okay, this is the expression for the energy stored in the charge distribution. Okay, thank you very much.